All right, so today we're talking about cloud. And let's give a little bit of background before we get into it, just touching on the details. Okay, so the big trend in data is that there's a lot more of it. And this is a nice graph. It's a few years old, but it gets the idea of it. Basically, data has been growing exponentially by something around 20 to 50% a year for quite some time now. And over the last decade, data volumes that organizations have to deal with have increased by, a factor of 1,000, more or less. And this is in terms of storage, transmission, processing. Businesses have to deal with a lot more data. A lot of it is about videos, right? Because videos are very, very data intensive. But that's not the only thing going on. The two basic kinds of data that get stored are structured and unstructured. So structured, if you have a monster pile of structured data, it's usually pretty easy to find what you're looking for because it's easy to search. So think of it as in terms of, for example, like a phone book. Even if a phone book has a lot of entries in it, you can very quickly zoom down to the one you're looking for, right? Because there's going to be some letters on the side that's indexed by last name. If you know somebody's last name and first name, you can find it very quickly in a phone book. But other kinds of data are extremely difficult to have structured sorting on. So for example, web pages. Web pages, there's not one single format for how a website can be set up. And so there can be a lot of different web objects on it. The text is hard to sort because every web page itself is potentially, its own big text document. And how do you sort that? It's not like a single entry for a phone book. So structured data is very easy to search. Unstructured data is difficult to search. And if you look closely at this graph, right here, I'm going to grab this and blow it up into Paint so you can see what I'm talking about. We blow it up like that. You can see red data is unstructured, blue data is structured. Well, if you look very closely at this graph, you can see, oh yeah, there's a little bit of blue at the bottom. So the blue data, sure, structured data is growing, but structured data is manageable. What isn't manageable is this massive growth in unstructured data. Storage media is actually pretty cheap. So you can buy a terabyte hard drive for something around 40 bucks these days. So even if your organization has a petabyte of data, well, petabyte is 1,000 terabytes. It's like $40,000. It's not that big of a deal. If you have many petabytes, all right, if you have 10 petabytes of data, well, that's about 40,000. What did I say? 4,000? 400,000. Which again, if you're an organization big enough to have 10 petabytes of data, is not that big of an expense, right? It's like a few IT employees for the year in terms of what you'd pay. The problem is with retrieving that data. If you have this massive pile of unstructured data and you don't have a good system in place for retrieving what you're looking for, then it's going to, every query you try to run on that is going to be extremely slow. It's going to be a giant pain. It just won't work. So this is the problem that businesses have to deal with. Not just the fact that there's a lot of data, but that the kind of data they have is very difficult to sort and search. All right. Now, a term you may have heard within the last 10 years or so, big data. And people still do say it, even though they probably shouldn't. So we understand right off the bat that big data means a lot of data. And it's a fair question to ask, well, how much data does it take to constitute a big data problem? Well, we can adopt as a working definition, right, or a simple understanding if somebody talks about a big data problem. You have so much data, or it's in such an awkward form, like it's so unstructured, that you need some kind of special techniques to handle it. And of course, this is a moving target, right? What was considered big data 20 years ago is, chances are, is pretty easy to manage now. For example, 1998, I first moved to Chicago and I got a little Windows XP desktop and I was very excited to have it. And the hard drive it came with was a colossal, mind-blowing 6 gigs of capacity, right? And at the time, this was basically in the pre-video era. So at the time, 6 gigs seemed like an absurdly large amount. And in fact, I never filled that hard drive. I had about 3 gigs of empty space, even with all the stuff I ever installed on it. So You know, and nowadays 3 gigs, that's nothing. You put that on a little flash ROM and yeah, you don't need a separate dedicated machine for it. So again, but if I had wanted to store, say, 10 gigs of data, well, at the very least, I would have needed 2 separate machines to do that. So for example, I might have gotten my regular desktop and attached some external hard drive to it. Something, I would have needed some special thing that wouldn't be in a regular off-the-shelf package. Okay, but again, capacities of these systems go up. 6 gigs is pretty easy to manage now. 10 gigs is pretty easy to manage now. Anyway, this is an old problem, right? There's always, as long as there have been computers, there have been requirements that exceeded the capabilities of those computers. So there have always been big data problems. This was just a name that got slapped onto it about, I don't know, 15 years ago. People said, yeah, let's call it big data now. Anyway, but the term should be avoided, right? It's just kind of corporate jargon, I guess, if you like. But it's inherently ambiguous. It's better to talk about the specific kind of problem you have. For example, do you have a problem that your organization is receiving data faster than it can process it? For example, there's a lot of uploads to your system or a lot of updates to your database. You can't handle that in real time. That's one kind of big data problem. Is there a problem that the amount of data you have is spilling over into multiple machines? For example, you have a traditional relational database system, which works great as long as you can keep all that stuff in RAM. But once the tables get really big and they can't be stored in RAM because they're too large for that, or they spill over into multiple machines, queries start running really slow. Do you have that kind of big data problem? So it's better to focus on the specifics than just to say, oh, yeah, we have a big data problem, and assume everyone will understand what you mean. Now, having said that, big data is useful as just a quick term for saying, yeah, we have a problem because we got too much, right? We got more than we can handle. So technological solutions to this, well, number one, you can get faster hardware. And yeah, that'll work, but it's pretty expensive. And it's only going to be a temporary solution, because if you buy a set of machines that's twice as fast as what you have now, then in a couple of years, you'll find yourself in the same spot where you've always been, because data is growing that fast. Another one, organization and algorithms. If you can set up your data to get processed better, for example, so one possibility, this is what Google does. I'll talk briefly about this. So they have what's fundamentally a relational database system, but even though it might be spilled over, right? So one table that they have in their database might be spilled over into many machines. What they're able to do in terms of updates is they group the data together in various ways, so they don't need to access that entire table to run a query on it, right? And part of that, for example, you might do things like isolating related groups of data within a table, or what else might you do? Segmenting tables so that each contains only what is commonly used. Or what else might you do? You might break up tables, break up big tables into very small ones. You might apply parallelism. For example, that's what they do in terms of providing search results. So for parallelism, simple example is if you have a big query on, say, a 1 billion row database table, right? You can break that up into 1,000 queries on, well, let's see, 1,000 queries on 1 million row database subtables. Okay, so you break it up into 1,000 subtables and run each query on a separate machine, and then combine the results afterward. Okay, so things like that, just basically approaching the problem in a different way. Not saying, yeah, we have a giant massive database table and any query we run on it, we got to search through the whole thing. That's not always feasible. Okay, so you have to come up with some kind of workaround so you can more quickly find what you're looking for. Okay, And toward that, again, they use something called horizontal scaling. So horizontal scaling is where you use large groups of ordinary machines. So sure, if you have a lot of data that has to be stored, you're going to need more hardware to store it on. But rather than having cutting edge, super fast hardware, the big players like Facebook, Amazon, Google, the sort of thing they do is horizontal scaling. They have large, tens of thousands of fairly ordinary servers, and problems that those servers have to handle. The big problems get broken up into a lot of little problems and processed in parallel. Okay. Now, cloud in general is the solution to this sort of big data problem. Part of it is that it's just more cost effective to have one big business specializing in this sort of thing. So we'll talk about it in terms of capacity management. Now, if you're running all these, however many servers you need to handle your business operations, if you're doing it in-house with your own machinery, you need enough capacity to handle peak traffic and respond quickly to any sudden changes in demand. So, for example, if your demand pattern during the day looks something like this, we're going to draw a fairly typical demand pattern. It peaks up in the morning a little bit, drops, peaks up in the evening, then drops, something like that. Okay, so we're going to label that network traffic. Okay, and this is, midnight over here, 12:01 a.m. to 11:59 p.m. All right, so during the day it looks like this. Now, if you want to have good service throughout the day in terms of being able to quickly respond to any sort of queries that come in, basically this is about how much you need to have. You need this much capacity on site. Not necessarily to have the machines up and running all day, but you need to have that many machines in place that can handle, handle typical peak plus some kind of safety margin. Okay, so you're going to need a little extra there. Problem is, this is constantly going up. Network traffic is going up. If your organization is fortunate enough to be surviving, then your needs are going to be going up 20 to 50% a year, perhaps. And that means what? That means you're going to keep needing to add on more and more hardware. This is a problem because, in general, the peaks increase faster than the average, right? So a typical organization might experience a peak to average ratio of something like 2 to 5 times. Okay, so your peak is going to, if your average is down here, right, in this particular example that I've drawn, the peak is up here, the average, just looking at it, I don't know, looks about something like that, and the peak is about twice as much, which again, fairly typical, but this peak is going to be growing faster. If the average goes up twice as much, the peak is going to go 4 times as much because the peak gets bigger twice as fast. This is a problem. It means you're constantly going to be needing to add more and more hardware. So if your average traffic is doubling in a year, you're going to need to have 4 times as many machines on hand. It's a big problem. Okay. So what cloud does, by having a whole bunch of different organizations with weakly correlated demand patterns, it's going to reduce that variability. So the cloud, right, there's still going to be some kind of trend to it all, but the cloud is going to see something that looks more like that, right? Which means it's going to have a much flatter curve, which makes all of its hardware requirements much easier to manage. If the average increases by a factor of 2, then maybe the peak is only going to increase by a factor of, say, 1 point or 2.2 or something. It's not going to go up that much. It's more cost effective for the cloud to provide that service to you. Okay. Other things, application and system changes. So if you put your stuff on the cloud, what that fundamentally means, you're going to lose a lot of control over how and where your applications and data are located. If you have it in a system under your own roof, you can very specifically say, this application is going to run on this machine or this set of machines, and we know how all those machines are set up to work together. We can super optimize that setup. Cloud, you generally do not have that capability. You don't have the power to look inside the cloud and control how everything is going to be set up. So it necessarily requires a different sort of attitude, different perspective on how to build these applications in the first place, which we'll talk about. So in general, that means you want to shift to modular applications. So rather than having big monolithic applications that are able to look into everything that other applications are doing, you want to deploy them as basically self-isolated modules that just interface with other applications, but don't need to know any of the details of how the other applications work. We'll talk about all this. Okay, that's the big picture though. Resource sharing on computers goes way, way back. As soon as the first people had designed a computer, pretty soon there were other people that wanted to run more than one application on it at a time. So this created the need for what was called time sharing. Basically, a computer would run one application for a while, say a payroll application, and then after that was done, they would maybe run some sort of data mining or, demand prediction kind of operation, something to crunch some big numbers in there. So that's the way it worked way back when. Now, nowadays, of course, we have our desktops, our laptops, whatever. It's no problem to run many applications at the same time. But early computers, this was not, this was a big crisis. So the other thing, computers are designed to handle peak demand. Just like you build up your network systems to handle peak demand, yeah, same thing for computers, right? Anything you're doing is probably not going to require the full capacities of your full capabilities of your device. And for example, if you do the Control-Alt-Delete on a Windows machine and look at all the applications that are running, typically you're going to see that it's running at about 5 to 10% of capacity. There's a whole lot of excess space in there that's not being used. So number one, storage, right? The amount of things that are being used in RAM or stored on your hard drive, typically there's a lot of empty space, right? I could look at this device here just to give an idea how much, let's see how much data I have on this. Not very much, right? So just this one that I've had for a couple years, 381 gigs out of 475 free. And I'm not even really trying at all to be efficient in how I store data. I have a whole bunch of duplicate files in my downloads, but still I'm, not, and with the operating system, I'm not even using a quarter of the hard drive. Okay, data transfer. Again, the amount of data that's being sent over the network or the number of connections that are being managed. Most of the time, you're setting up your system to handle peak demand. So on all the other times, there's going to be a lot of empty space. There's going to be a lot of idle capacity. And computation, same thing. For that Control-Alt-Delete on Windows machines, most of the time CPUs are idle. They're only using like 5 or 10% of their capabilities. Now, problem with all this, again, you still have to be available for peak demand. So if there's a bunch of stuff going on, then boom, suddenly all that stuff becomes busy. But most of the time, yeah, there's excess capacity. So same kind of thing with cloud. They have a lot of machines. Most of the time, any individual user is not putting a big demand on the cloud system, so they can handle a lot of things going on at the same time. Now, cloud computing, besides having excess capacity, requires a few key things. Number one, high-speed data transfers. So if a business has many gigs of data up in the cloud and they want to retrieve it, they need to have the ability to do so fairly quickly. This was a bottleneck for a long time. Up until about 10 years ago, businesses said, yeah, you know what, we're having big data problems, but considering how long it takes to send and receive our data and other problems about security, this cloud thing's kind of dicey, right? So, but as the cost of managing their own data kept going up and the ability to retrieve data faster came around, then businesses came around and said, yeah, okay, we can do this. This makes sense. Of course, they also need elevated security. A cloud system is going to be holding data for a bunch of other users, and those, it's going to be allowing those users access to the system. It's going to need more security than a typical on-premises system. And last, standard interfaces and service-oriented architecture, basically how you design your applications to be modular, which we'll talk about. Okay, so starting with demand smoothing. So the big player, Amazon, excuse me, Amazon has over 1 million customers. It is the biggest public cloud system. And those individual users have widely varying requirements, right? So if you're a business in North America, you get a lot of traffic during the day, probably not so much at night. If you're a business on the other side of the world, you get traffic, again, the opposite schedule. And different businesses have different work cycles. Some of them are busy on the weekends, some are busy during the week, some are busy at Christmas, some are not. You get the idea, right? Tax services, very busy around the quarterly deadlines, the annual deadlines. But overall, the collective requirements are pretty smooth. Just like I said, the individual sites will have a fairly high peak to average ratio. Something like Amazon would be much flatter. In fact, from inside numbers, Amazon doesn't come out and say exactly this is what we get, because it varies from time to time. But people on the inside of various interviews have suggested that something close approaching 70% is what Amazon is seeing in utilization. So that means they're using at any given time 70% of the servers that they have. Their demand is stable enough that most of the time they're using most of their servers. And that's a wonderful thing. That means they only need to have 1.5, right? So 1 divided by 0.7, it's about 1.5. They need to have 1.5 servers for every server worth of service they're providing. For a typical non-cloud provider, that utilization number is about 15 to 20%. So for those guys, it's going to look more like this. They're going to see something like, okay, and this whole shape here, right, if you box this up, and we fill that, that's the part they actually need when they need it. And this is maybe only 20% of the area. This 80%, that's idle. So that means, in essence, they need to provide 5 servers for every 1 server worth of action they're getting, or maybe 7 servers if it's down to like 15%. So Amazon, that's why they can provide the capabilities much cheaper. Amazon only needs to have 1.5 or so servers on hand to provide a server's worth of services. A typical smaller business would need to have maybe 5 or 7 servers on hand to provide the same capabilities. So, consequences for these large-scale cloud providers: basically, they can serve more users, basically do more per unit of hardware that they have under their own roof. Also, benefits: it's easier to schedule system management. So things like downtime scheduling, when servers are taken offline, when they're put back online, when they're going to schedule patches, other routine maintenance, all that you can schedule more effectively because you don't have to deal with these sharp, sudden changes in demand. And of course, better quality of service, because for a cloud system, it takes a big traffic spike to be noticeable. Amazon is so much bigger that it would take a really, really, really big event to noticeably hurt Amazon's quality of service. The last time that happened as a big thing was on Prime Day a couple years ago. And yeah, that kind of affected their system. They weren't ready for it, but now it's been pretty good. They added in more capacity. So this is basically how the system works. If you're interested, I have an article here from a few years ago, but it's still pretty relevant at the level that they bring it in. I mean, yeah, sure, some of the details in Amazon have changed, but the big picture is correct, and Amazon's not going to tell you a whole lot of detail about stuff that happened in the last year or so anyway. All these organizations tend to be secretive about their special sauce. Okay, so how does cloud work? Well, I'm going to lift this over to Paint as well. We're going to capture that. And then I can. Okay. So again, old picture, there's a couple things that have changed, but the gist of it is correct. So you have a bunch of users using various applications, right? So these guys, one of these says HTML, or a couple of them say HTML, and one of them is sending email, whatever. I don't know why this doesn't want to. There we go. They have users using various applications. They all connect at the same website, Okay, if you like, you can think of this as Facebook. That's fine. And they go through a firewall, they go through a load balancer. So here, so these days, this stuff is all kind of integrated together, but once upon a time, there were separate pieces of hardware. So inside Facebook, users connect to a server chosen by Facebook. So whatever you're doing at Facebook, they have your data stored somewhere. They're going to connect you to that if you need it. If you want to run a particular set of applications, they'll connect you to the server where those applications are available and running. So each of these cloud instances, group of servers running the same application. Okay, so typically you want to have, for any server, you only want it to have it run one application, and you're going to group those in various ways so that if one of those servers crashes for some reason, another one in that group can quickly pick up the load. But wherever you are, this is what happens. Key things. To the outside user, you are just connecting to the same system as everyone else. You only need to know the URL. You just go to facebook.com and Facebook takes care of the rest, right? The cloud takes care of everything on the inside. This is the real magic of cloud as far as the user's perspective. You go there, show up, whatever's going on back here, you don't have to worry about that, right? This is a good example of a modular system. All I know, as long as I go to facebook.com and process, and enter the commands in the correct way, I click on the thing or put the right text into the search box, whatever I'm doing, everything else is going to work. I just need to know how to work the interface, and Facebook is going to take care of the details. All right. So basically how it works, there's load balancing in various ways. Cloud systems want to make sure that none of the servers get too busy and none of them are totally idle, because if they are totally idle, then why are they even powered on? So anyway, the cloud system is going to dynamically assign connections to different cloud instances. Basically, it's going to figure out how many servers it needs to have on hand. It's going to assign connections to those at various times during the day. As demand starts tapering off, they might start grouping together some of those. They might start shutting down some of the servers after transferring the connected users to other machines. So they more or less only need to keep on what they need to keep on. And all of that is going to be opaque to users. You're not really going to experience that. You're just going to say, oh, I have access to my stuff. Great. Don't really care what machine it's on. So cloud instance is a virtual server instance, which essentially means a group of servers that's effectively treated as one unit. So as far as the end user is concerned, again, you go to Facebook, you're going to get directed. Your stuff is on some machines over there. Doesn't really matter which one. You don't care about the connection to the particular machine. Facebook's going to handle that for you. Now, again, in various ways, it's usually a good idea to confine applications to single servers rather than having each server carry a whole different mix of applications. The big thing for that is managing quality of service. So let's go back to Paint here. So I'm going to say when I have a bunch of servers running the same application, you'll see this part here. Imagine if I have 100 users running Microsoft Excel, okay? And I add on 100 users running who knows what applications, right? Or better yet, if I have 100 users running a mix of applications, it's a wild guess what another 100 would be like, right? So it might be that they're running low demand applications like Excel or Microsoft Word, something like that, but they might also be doing highly demanding applications in terms of data transfer, like live video streaming, something like that. So if you let every server run the whole mix of applications, quality of service is going to be a lot harder to track. You don't know exactly what's going to happen if you throw on another 100 users. However, if I have 100 users running Microsoft Excel and add on another 100 also running Excel, it's a lot more noticeable. It's a lot more, it's not going to be a wild guess. Okay. Basically, I pretty much know what to expect. I can say those 100 Excel users are going to be a lot like the previous 100 I have. Chances are. Okay. There might be a little bit off here or there, but for sure, adding 100 new Excel users to a group of already 100 Excel users, I know what that's going to look like in terms of data demand. If I have a complete mix of applications, no idea. It's a lot harder. Other things in terms of security, just generally speaking, if I have a bunch of people all using the same application on one server, I have a lot more data going on about what that sort of traffic should look like. And if anything is standing out, then it's going to stand out more. Whereas if I'm running a bunch of different applications, then I'm going to have packets from a lot of different applications. They're going to look different to automated security tools. They're going to be trying to connect to different application ports. There's more stuff to manage, and it's going to be harder to verify that, oh, this particular stream of data looks weird, just because there are already a lot of different streams of data built in. And any backups that you have are typically going to be located on another cloud instance. So on another group of servers, just in case there's some sort of problem that affects an entire group. It would be, it's analogous to say, if you're storing suppose you have a bunch of family photos that you want to keep safe, right? And they're digital. So sure, you have some on one machine, but you don't store all of your same backup copies on another machine in the same room, because what happens if there's a fire, if there's a flood, something, then you're going to lose both right away. So yeah, typically if you have backups, you want to keep some distance between those copies. Anyway, where the data is stored, typically it's going to be on a server farm. Think of it as just basically a giant warehouse full of servers, and it could be in another country depending on the requirements. And redundancy, again, there's a lot of backup capacity provided in cloud. So duplication for any data you have, typically you have at least a triple copy of anything that's stored. So not only can you recognize if something is wrong with one of the copies, but in some cases, you can correct what's wrong with it as well. You can reconstruct an original. And you want to have duplicates available for continuous access. So in a variety of ways, if you want to access your data and a machine goes down, well, they can quickly redirect you to another machine where it's located. Or if there are a bunch of users that want to look at the same data, it's going to work a lot faster if it's available on multiple server machines. So those are the sort of features that are built into cloud, and they allow, again, more reliable operation and handling scale for large groups of users. There's three models for cloud, three big ones: public, private, and hybrid. So public cloud, this is what most people think about when they think of cloud. Basically, you have some big cloud operation, like say Amazon, they lease usage to others. So for a price, you can show up and use the cloud service, and basically it's open to anybody who can pay. Private cloud, it's a little different. It's a cloud architecture where the hardware only allows access to a particular enterprise. Now, a lot of times when people talk about this, they mean some kind of on-premises system. So for example, if who's an organization, suppose Target has a whole bunch of servers inside that they manage as a cloud, that private cloud would only have access to Target itself, right? It wouldn't be out there shared with the public. It would be Target's using Target's cloud to store Target's data. However, there is something called a virtual private cloud, where that means you essentially have the security of a private cloud within a public cloud system. So that would be Amazon saying to Target, okay, we're going to wall off this part of our system. We're going to reserve, say, 10 or 100 or 1,000 servers, whatever, and only you are going to use those machines. Now, the downside of that, of course, you're going to have to pay more. If you're reserving a specific machine count, you have those available for you whenever you need them. Nobody else has access, but you have to pay for the entire amount of what you're using. You don't just get to pay for a fraction of that like you would in normal circumstances. And the last one is hybrid cloud. So a hybrid cloud is, again, a hybrid, mix of private and public clouds for use by one enterprise. And this is a fairly common setup. A lot of organizations will do this. For example, if you have sensitive data like financials or emails, maybe you don't want to keep them in a public cloud where you're concerned they'll leak out somehow. But if you have other things like marketing releases or images that are going to get posted up on your website that people are going to see anyway, yeah, maybe that you store in a public cloud. You're not really worried if people can peek at it. And you keep a backup copy of the data inside your own organization, so if something goes wrong, you can still access it. Okay, so those are the big three: public, private, hybrid. Next thing, how cloud services are provided. So there are three big structures, three big groupings for that: infrastructure, platform, and software as a service. We'll talk about those. Looks like we'll have some lecture left over Friday, so this is taking longer than I had expected. That's okay. There's time built into the system. Okay, so the big three: infrastructure, we'll start with that. So infrastructure as a service means you get the hardware, so-called bare metal servers, right? There's not going to be anything on them. So the good thing, total freedom to install operating systems, even custom operating systems if you want to. Total freedom to install any applications, okay? But the downside, you have to do all that, okay? And maybe your organization, maybe they're not really interested in designing their own applications. Maybe they're definitely not interested in designing or updating their own operating system. So this, move that down there. This is one option. Okay, and again, if you're an organization that requires a lot of customization for your system, yeah, maybe this is something you want to do. However, other organizations might choose platform as a service, which means you get the platform, hardware, operating system, maybe some generic big applications like a database, a relational database system, relational. Okay, that's the sort of stuff you get the platform. So total freedom to install any applications, okay, even custom ones, but the platform is what it is. You can't really check, you can't customize it that way. You'll typically have a set of options. For example, you can choose your preferred OS, but can't really, you know, tweak it, customize it. Okay, so that's the next one. So I'm going to box this around because why? Because everything that you get in infrastructure, you get in platform. But, you know, you get the hardware, you get the operating system, but you don't have the flexibility to change it. What changes is this stuff on the outside. You can change which applications you're running on it. I'm going to move this up a little bit. Okay, the last one, where do you in blue? Okay, the last one is software as a service. Okay, in software as a service, everything is already there. Hardware, operating system, applications. You choose which apps to run and some options for how they run. But you can't customize them beyond that. Okay, if you want a good example of that, Facebook, right? You show up on Facebook, there's a bunch of applications already there, you can use them, but aside from picking some check boxes on who you want to see stuff and how you want them to run, you can't go around and dig into the applications and really change them. Okay, so again, these are the upsides and the downsides, right? For example, infrastructure as a service, you have complete freedom to change anything you want, right? The hardware is there, you can't change that, but beyond that, whatever you want to fix, you can. Run whatever operating system, customize it, design applications, customize them, run them, whatever. Platform as a service, some of that's taken away, right? You don't have the freedom to do it, but you don't have to worry about doing it either. So for example, all these things like operating system patches, the system is automatically going to handle that for you. Okay, again, some generic big applications, like if you go to Oracle, for example, Oracle is big in the relational database game. One of the things they're going to give you is one of their generic relational database applications. But beyond that, you can put in anything you want. And a lot of platforms, you might not even get that. You might not get anything except the basic operating system. Last, software as a service. Okay, software as a service, you show up and you use it, which means management headaches are basically nothing. You don't even have to worry about designing applications or picking which ones to run. You just show up and you use what's there. The downside is there's not much in the way of customization. So if it turns out that those applications are not really useful for your organization anymore, you want to go in a different direction, well, unless you have the new applications under that roof, you're either stuck with it or you got to go to migrate everything to a different system, which is a big headache. Okay. So again, management workload for clients. Infrastructure is a lot of work to get that up and running. Not all businesses want it, but for some, it's worth it in terms of the flexibility. Software as a service, on the other hand, very little management workload. You just show up and use the applications, but again, then you don't have that customization potential. Okay. Next thing, service-oriented architecture. So I'm going to take a minute and explain this in a different context that maybe will help people get it. So first, let's talk about applications themselves. Just conceptually, you could have a big monolithic application, Monolithic is a fancy word meaning one rock. So it's all just one structure. And suppose there are different things happening in that structure. Draw some boxes. And in various ways, these boxes interact with each other. But because it's a monolithic application, it's hard to keep track of what's happening where. Okay, so you have various things going on inside the application, but anytime you change one, you're not sure if it will affect how the others run. And you need to check that. Okay, so I'm going to give a non-computerized example because I think that's something that people can understand a little bit better. So imagine if you have a thermostat on your wall. Okay, let's get rid of this for a second. You have a thermostat. When you push the buttons or turn the dial, the heating system, heating or AC system gets a signal and adjusts the temperature in your house. Okay, we know what a thermostat is. Now, what's going to happen you got a little box here, right? And that goes down to your heating system here. So I'm going to draw that very big. Because this system is set up to be modular, right? I know if I send a signal here, right, it eventually gives some feedback and tells you like, okay, we understand, we're going to do whatever. So here, just call this thermostat. It does what it's supposed to do. And I don't need to set this up I don't need to know how the heating system works, right? All I need to know is that the thermostat is connected correctly to the right electrical stuff in there, works correctly. This means if something goes wrong with the thermostat and I want to replace it, I can just unhook it from the electrical connections and attach a new standardized thermostat, possibly of a different manufacturer, right? A different model or manufacturer. Okay, it doesn't have to be the exact same one. I know as long as the wires get sent out the same way, the signals get sent out the same way, I can do that. It's easy to change, right? So this modularity makes the system easier to change, right? Imagine though, if I said, oh, this thermostat, in order to do it, I not only need to replace the thermostat itself, I need to dig into the heating system, verify that the electrical signals are the correct way. I need to get them with the same frequency, the same voltage, whatever. If you needed to verify all the inner workings of the heating system as part of replacing the thermostat, it would be a huge headache, right? You wouldn't want to do that. Same thing with applications. So if I have a big monolithic application where all of this is essentially bundled together, I change one part of it like the thermostat, I have to dig through the application code and verify that everything that I changed in the thermostat is still going to work with the rest of this. But if I've set it up to be modular, if I've taken all those little functions within that big monolithic application and broken them up so that I know, here are the only things I need to worry about. I need to worry as long as if I send a standard signal to the heating system, it's going to work the way it's supposed to, right? So modular design, don't need to dig around in the system for every change as long as the interface format requirements are met. Okay, this is how it works with heating systems. It's the same idea with software. As you have a modular system, if you can say, you know what, as long as the data that's being sent is getting processed and is getting sent in the correct format, the system's going to process it in the correct way. So then all you have to do to replace part of the system is replace whatever's on one side of that interface. You don't have to worry about everything on the other side. Okay, so back to cloud. This brings us to a concept called service-oriented architecture. So in this case, services mean small software components that perform a simple task. For example, accepting a credit card request, transaction request, or adding things to a shopping cart, stuff like that. So all of those little application components, they work as modular objects. Basically, they send and receive data through these standard interface formats. And just like the example of the thermostat, that allows you to have these services interact with each other. It allows you to reuse services or deploy them in new places or replace them with other ones, regardless of what else is going on. So for example, I have a simple web system, right? I have a few services, shopping cart, checkout, and I don't know, security, whatever. Okay, so shopping cart, credit card transaction, and as the last one, verification, right? So very simple things. Whenever I press click, right? Press click to buy, what has to happen? Well, convert shopping cart contents into a credit card transaction, right? With an amount. How much is this going to cost? And who, amount, and user. So that's something, right? So this shopping cart has to have a fairly standard format, and it's going to contain a bunch of items. When I'd say click for buy it now, all that is going to get compiled into one amount total because that's all the credit card transaction really needs. So the credit card transaction then can do simple things like send user, amount, right? Credit card numbers, possibly item type, possibly. And that'll get sent to verification. So the system can again say, oh, this transaction looks plausible, or this transaction looks sketchy. Let's send back a hold on the credit card, right? So these, very simply, you know, they only need to know the data that they get. As long as the data is sent in the proper format, this shopping cart application doesn't need to know the mechanics of the credit card transaction. Likewise, the credit card transaction application doesn't need to know the mechanics of the verification application. So I can change any one of these. I can pull out, you know, change to a new cart style, and I don't have to update any of this. Or I can allow different additional credit card companies, right? I can have a bunch of extra ones there, and I don't need to redesign the system for that. Okay, so I can say connect with different CC firms without redesigning everything. All right, and that's the sort of neat thing you can do with these modular designs. It makes it very easy to change systems, makes it very easy to scale them out because you don't have to redesign the system. You just say, well, as long as you conform to our interface style, we're good. We don't have to change too much. Okay, and so web services are a way of specifying the sort of data that has to be sent. So for example, if I'm sending a credit card transaction, there's going to be a few specific things that get sent, right? So certainly, so these get sent as objects. So they're going to be username, user address, CC number, CCV code, right? The security code, the amount, expiration date, okay, and possibly a list of items. But these things are typically for sure, right? These things here are about absolutely what has to get sent. And these other things are typically sent as well. I should add also possibly item type. Okay, so you might say as a credit card company, you're more concerned about stolen electronics or jewelry. And so anything that gets sent, you know, with that kind of item type, you're going to give it a little extra scrutiny. So that might get sent along too to a verification system. All right, so all of this gets bundled together as a JavaScript object typically. The typical object language is something like JSON, which is a JavaScript compatible one, where all of this data is essentially constructed as a JavaScript object and sent along. Or you might use XML, which is a lot like HTML. It's tag-based, but it's less used now because it takes up more space. Anyway, and then web services are simple ways that you can manage this sort of exchange of data. All right. So again, standard service objects, when you have data interchange between these small service applications, You might send data to a credit card verification. You might send it to shipment tracking, for example. As long as you enter in the proper tracking number, you get the correct shipment information. Social media links. If you connect to one system, all you have to do is send the appropriate data and you get back whatever you're looking for. Even site search capability, right? So you go to any site that has a search feature on there. Of course, you enter in a string of text. As long as you've entered in a string of text, it's going to try to match that to what's on the site. And in all these applications, the modularity is provided by, number one, specifying proper input formats. As long as you adhere to them, you get some slug of data back that your application is going to process correctly. Okay. Talk a little bit more about modularity. So these early network systems, I mean, think way back to like the 60s and 70s, they were often what's called tightly coupled. So that simply means they were designed with specific machines, specific configurations in mind. So for example, you had two pieces of hardware, you knew exactly how they were going to work. If they were, for example, the same hardware and you knew they were running the same application and you knew that's all that there was ever going to happen with those, then you could skip a lot of steps of the data reformatting because you essentially knew, well, what's coming out of this one machine is exactly the format that's going to be needed by this other machine. So maybe you didn't have to have that sort of translation step in there. But as the networks got bigger, new and different machines got added on, you couldn't take that for granted anymore. All of a sudden, you needed to say, oh, we have to put all this data in a standard format so that other machines can read it, because otherwise we have to set up custom interfaces between every pair of machines. It's a huge pain in the ass, right? So these early systems, they were tightly coupled, which basically means there are a lot of system dependencies in place, that any part of the system depends on other parts of the system to run a certain way. And those early systems, all things considered, they ran pretty well, right, for the hardware that they had, but they were difficult to change, expand, otherwise modify. Anything you want to make different could break up some of those dependencies and require a lot of work to see what was, how to make it work again. Now, over time, data growth kept on getting bigger and bigger and bigger. So around, in the 70s, you might buy a set of machinery and have it be working the way it's supposed, working the way it's designed for several years. And yeah, it would be pretty old and creaky by the end, but still, you could make it work. They got a lot of mileage out of the machinery that they had. But when your data requirements are growing by 50% a year, keeping that sort of stable system in place is no longer an option. Growth is mandatory if you're going to survive. So expansion isn't optional anymore. You need to focus more on the ability to expand or change your system rather than trying to make it work optimally for a fairly stable set of requirements over time. So what you started to see was systems would be designed with more modular hardware components and more modular applications. So the first thing, of course, you design modular hardware, and then you hope that you could run the same application on everything. But even that eventually became a problem. Applications had to become modular as well. They got bigger, more complicated. We're processing more data. There were more copies of them, more interactions between them. Now what we're seeing is even what you might consider to be modularity across systems. For example, Cisco DNA that we talked about the other day, networking as a service, they're going to provide some sort of modularity. They do all of their network stuff off premises for you and just send the results. And again, then essentially your entire network functions as essentially as a module. You just see what comes out through the standard interface on the other side. Now, system dependencies are very undesirable for cloud. Why? Well, because the cloud will not have the freedom to deploy parts of the system wherever they need to be done to keep things cost effective. So in practice, having modular systems and applications are pretty much required before you migrate your stuff to the cloud. So again, tightly coupled systems, they're going to be higher performance for the hardware that they have, but they're going to be difficult to change because any change to the system might affect other parts, and so you need to be aware of that. But data grows faster. What happens? Well, you can't assume that your system will be stable anymore. You have to plan for change. You have to build that into your systems. So you build a more modular system where change is relatively easy. And again, in particular for the cloud, the ability to deploy component pieces on different servers. For example, if there's a very busy part of the system, you might cache part of what it does in RAM so it can respond super fast. The ability to make changes like that is really part of what gives cloud its edge. And so if you take that away, if cloud has to run the same way as an ordinary business does, yeah, you'll get some benefits of economies of scale, but you won't get all of them. Cloud works best when the cloud can take portions of applications, deploy them wherever it wants within the cloud. All right. So once an organization adopts service-oriented architecture and web services as its standard approach to designing applications, a lot of things become way easier. So number one, it's easy to divide applications into components. Why? Because if they're already built up as services in the first place, they're already a set of these modular applications. There's nothing that you need to do to further divide it. Number two, transfer components to the cloud. For example, some of your things you can run in the cloud, some of the things you can run on premises. You have that flexibility. Or you can use other components available in the cloud. So for example, there was an Intuit case study that I looked at not long ago where they were talking about how they implemented their chatbot feature. And if they had to design it themselves and integrate it, in a custom way with all of their existing applications, it could have taken years, they said. But because they'd already designed their applications in a modular way, when they went to the cloud, there were a bunch of chatbot services already available. They looked at them, they picked one, they specified what needed to be integrated as far as the interface itself that say these key phrases pointed to these key topics in their database. They had it up and running inside a couple months. So it becomes much, much easier to use components that already exist or to make copies of them, whatever. So simple case for that. I guess this will be about the end of our day. We'll do a case here. So suppose here's Amazon and here's me. I'm selling some stuff through Amazon, right? I don't know, me, the seller. Okay, and here's Amazon. Now suppose initially all I want to do is post ads on Amazon. Okay. Initially, I just have a product listing on Amazon. That's fine. Okay, maybe that's how I do it to start with. And so anytime an order comes in, I handle the shipping, right? I actually bundle up the stuff myself and I take it to FedEx or UPS or post office, whatever. I drop it in the mail. And that's all I have to worry about. But maybe I want to do some other stuff, right? Maybe I want to integrate it with some other operation, like say Salesforce, where I can do some customer relationship management, some other advertising. Okay, I could do that. I could integrate it. So I'm going to put in Salesforce here. And then I send my data to Salesforce, right? Maybe I still keep my listing on Amazon, but that's all there. Okay, and I'm still handling the shipping. But eventually, maybe I don't want to handle that shipping anymore. Maybe I want to tell Amazon, you know what? Send it to UPS. Anytime this happens, okay, anytime shipping has to happen, sure. You can contract with UPS. I'll send you a batch periodically. Amazon tells me when they need more. Okay. Okay. Amazon can handle this part for me, right? And somehow that's handled by another organization. What else? Credit card transactions. Maybe in the early listings, right? I put something up on Amazon. Maybe in the 90s, I'm having people send me checks, right? I just advertise it on Amazon. People send me checks. I bundle up the checks, take them to the bank. But instead, hey, you know what I really want to do? I want to interface that with credit cards and bank accounts, right? So let's say, whoop. Credit card companies. bank accounts, whatever. And I'm having Amazon automatically send stuff that way. So all of these things that perhaps one at a time I used to do by hand, then whenever I need them to be changed, I can make some kind of update to the system and say, you know what, I'm not going to do this part anymore. I'm going to let that be handled in some automated way. So modular systems allow users to update portions of the system, handle them differently without affecting the whole operation or reusing standard services, right? So for example, with credit cards, I'm not going to develop my own custom credit card transaction handler, and I'm sure not going to develop my own verification process, right? I want to use one that already exists somewhere, and it's great that it does, right? So then I don't have to worry about that problem. I can just use a standard credit card process there. Same thing for UPS, right? I don't want to have to design that whole system myself. I just want to be able to show up and use what UPS already has. So as long as I follow the standard format of saying, here's the shipping option I want it sent, 2-day express or whatever, and the package is 5 pounds and has such and such dimensions, UPS can automatically tell me how much it's going to cost and how it should be shipped. It'll give me a tracking number that I can send to users. All of those little features are built in without me knowing anything about these systems, right? I don't need to know anything about what goes on at the credit card company, don't need to know anything about what goes on at UPS, don't really need to know anything about what goes on at Amazon or what goes on at Salesforce, right? All I need to do is understand the interface and the work will happen. Okay. So that's the thing, right? That's all of this modularity. And it seems like a good break point. We'll come back on Wednesday. Those of you who are here, you can hear the rest of this. Those of you who aren't here can watch it as a recording. Any questions about any of this stuff? I'm going to stop the recording.